This video we're gonna go through the homework 12. So let's look at first problem 10.59. So we have a fluid with viscosity equals to 10 to the negative 6 meters squared per second, and the density is 800 kilogram per cubic meter. And the pipe here is 8 centimeter galvanized iron pipe. So we're gonna need to find the flow rate for this pipe. So first thing, we're gonna write down the information we have. So we have the viscosity, which is 10 to the negative 6 meter per second, and density is 0 equals to 800 kilogram per cubic meter. The diameter of the pipe is 8 centimeter, so it's gonna be 0.08 meters. And we have a slope of 1/10, so the length between, let's say this is 0.1 and 0.2. The horizontal distance is 30 meters and the slope is given. So if we say Z1 is 0, then Z2 is gonna be 1/10 times the 30 meters, so will be 3 meters high. And the length of the pipe will equals to the square root of Z2 squared plus the 30 meters. So it gives us 30.14 meter. Okay, so now we can write down the energy equation between 0.1 and 0.2. So P1 is not 0. V1 squared over 2G plus C1, which should be 0, because we set Z1 equal to 0 and Z2 is equal to 3 meters. And P2 is not 0, so it's P2 over gamma plus V2 squared over 2G plus Z2 plus the head losses. Notice the velocity should be the same for the 0.1 and 2, so they can cancel out. So the only term we have here will be P1 over gamma equals to P2 over gamma plus Z2 plus the head loss. So, and the pressure is given here, which is 150 kilopascal. And gamma, which should be rho times G, so is 800 kilogram cubic meter times 0.81 per kilogram equals to 0.2. The pressure is 120,000 pascal. It should also divided by rho times gamma, so rho times G. And Z2 is 3 meters. So if we do the calculation here, the head loss is 0.823 meters. Now, because we are given the pipe informations, we can use the Moody's diagram to find the F and then find the velocity. Okay, so HF should equals to F times L over D times V squared over 2G. Okay. So the next step, we're gonna find the F here. So to use the Moody's diagram, first we're gonna find the relative roughness, Ks over D, which Ks you can find in table 10.4. So it will be Ks equals to 0.15 millimeter, and it will be 0.5 times 10 to the negative 4 meters. So Ks over D equals to 1.5 times 10 to the negative 4 meters divided by D, which is 0.08 meters. So the relative roughness is 1.9 times 10 to the negative 3. Okay. And the next parameter we're gonna find is ED times F to half, power of 1/2 equals to D to the power of 0.2 divided by the viscosity times 2G times the head losses over L times to the power of 1/2. So this term you can find on the top horizontal axis in the Moody's diagram. So if we do the calculation, D is given 0.08. The viscosity is also given, which is 10 to the negative 6 meter. Squared per second times 2 times G. And the head loss is 0.823 meters. And L is 13.40 meters to the power of 1/2. And this value will be 1.66 times 10 to the power of 4. So we're gonna use the Moody's diagram. And you will find the F is about 0.025. Okay, now we have the F value. We're gonna substitute in this equation here. So equals to 0.025 times L is 13.14 meters. The diameter is 0.08 times V squared over 2G. Okay, so the V should be 1.312 meter per second, and the Q should equals to the velocity times the area of the pipe. So it's 0.312 meter per second times pi over 4 times the diameter, 0.08. So it should be 6.59 times 10 to the -3 cubic meter per second. Now let's look at second problem. 10.60. A pipe is to be designed to carry out crude oil. The specific gravity here is given as G equals to 0.93. And the viscosity is 10 to the -5 meters squared per second. The discharge is 0.1 cubic meter per second. The head loss per kilometer is 50 meters. So we can say if the length is 1,000 meters, the head loss will be 50 meters. Okay. So we're gonna to find a reasonable pipe diameter, and then we will calculate the power output from a pipe. Okay. So for this kind of problem, we need to assume a friction factor first. Then we're gonna calculate the Reynolds number and find the friction factor again, and and gradually make the friction factor become closer to the real answer and determine the diameter of the pipe. So the first thing we're gonna do is assume a friction factor. So we usually start with a kind of common friction factor, which is 0.015. Okay. Then we're gonna use Darcy's equation. D equals to F times L times Q squared G times pi squared times the head loss to the power of 1/5. Okay. So we have all the informations here. So F is 0.015. 8. The L is, because we choose 1,000 meters, and the Q is 0.1 cubic meter per second, and G is 1 gram times pi to the power of 2, and the head loss for 1,000 meters should be 50 meters. Okay. To the power of 1/5, and this will give us a number of D equals to 0.19 meters. So now we're gonna use this D to find the Reynolds number. RE equals to 4 times Q over pi D times the viscosity. So Q is given D is 0.19 meter, and viscosity is 10 to the -5 square per second. Okay. So for those values, the Reynolds number should be 6.7 times 10 to the power of 4. Okay. Now we're going to use the Reynolds number to find the new friction factor, which is 0.25 over log of Ks over 3.7D plus 5.74 over Reynolds number to the power of 0.9 to the power of 2. Okay. And this will give us 0.021. Okay. So this is our new friction factor. The next step, we're gonna keep repeating the process. So now we're gonna do the calculation of D again. It's to 0.021 times 8 times 100,000 meter times 0.1 cubic meter per second, 9.81 times pi squared times 50 meters to the power of 1/5. Okay. So this will give us a new D equals to 20.3 meters. Sorry. It should be 0.203 meters. Okay. Then we're gonna do the calculation again for friction factor. Ks 3.D plus 5.75 over Reynolds number times to the power of 0.9, and the entire thing to the power of 2, and this should give us 0.021. So this F here, the new F, is equals to the old F, so we can see the answer of D is already quite close to the real D we need, and because we have D of 0.23 meter, it should be about 20.3 centimeter, and we will need a pipe that's a little bit larger than this number, or we can say it's next larger pipe size. So given the problem gives us 20, 22, and 24, so we should choose 22 centimeter pipe. Okay. The next step, we're gonna need to find the power output from a pump that need to maintain this flow. So the power should be P equals to Q times gamma times the head losses. Okay. Q is given 0.1 cubic meter per second. The gamma is 0.93 times the gamma of water, which is 9810 cubic meter. Okay. And we need to times head losses. For 1,000 meter, it should be 50. Okay. So the power is 45.6 kilowatts for each kilometer. Of pipelines. Now let's look at problem 10.71. So this problem is asked us to find the power of the pump for this system. So we have two reservoirs here. The information given is the rho equals to 940 kilogram per cubic meter, and the viscosity is 10 times negative 10 to the power of -5 meter per second. The length of the pipe is 150 meters. And if we said this is 0.1 and this is 0.2, the elevation, the Z1 is 100 meter, Z2 is 112 meters, the Q is 0.3 cubic meter per second, and it's a steel pipe. So if we use table 10.4, we can find that the relative roughness is 0.046 millimeters. So it's 4.6 times 10 to the -5 meters. Okay. So we're going to start with the energy equation. P1 over gamma plus V1 squared over 2G plus C1 plus the head of pump equals to P2 over gamma plus V2 squared over 2G plus C2 plus the head losses. Okay. So because we're choosing the water surface, it has the 2 points, P1 and P2 is 0, V1 and V2 is also 0. Only leaves us the elevation term, the pump head term, and the head losses. So the elevation is 100 meters plus the pump head, and equals to the elevation at point 2 is 112 meters plus the head losses, which is the entrance coefficient plus the friction losses F times L over D plus the coefficient of exit times V squared over 2G. So the V here is the velocity inside the pipe. So because we have a kind of entrance and exit. Okay. So this is for the K lowercase e for the entrance and the K uppercase E for the exit. Okay. So if we move the terms here, the pump head should equals to 12 meters plus 0.03 plus F times L, which is 150 meters, and the diameter is 30 meters, 30 centimeters, so 0.3 meter. And the exit is one here. It's 2G. Okay. So the V here, because we have the Q and we have the diameter, so V equals to Q divided by A. And Q is 0.3 cubic meter per second. Area is pi over 4 times the diameter, which is 0.3. 2 squared. So the velocity is 4.244 meter per second. And V squared over 2G equals to 44 second to the power of 2 over 2 times 0.81. So the velocity head should be 0.9181 meters. Okay. The next step is to find the friction factor F. So we're gonna find the Reynolds number first. RE equals to V times D over gamma. Over the viscosity. So the velocity is 4.244 meter per second. Diameter is 0.3 meters. The viscosity is given, which is 10 to the negative 5 meters squared per second. So the Reynolds number is 1.27 times 10 to the power of 5. And the relative roughness Ks over D is equals to 4.6 times 10 to the negative 5 meter over 0.3 meter. So it's 1.53 times 10 to the negative 4. So if we move this diagram, we will find the friction factor is about 0.0165. Okay. Now we have all the information, so we can find the head of a pump equals to 12 meters plus 0.03 plus 0.0165 L over D plus 1, and then the entire thing times the velocity head. So So the pump head should equals to 20.52 meters, and the power should equals to Q times gamma times the head of pump. So Q is 0.3 cubic meter per second. Gamma is the specific gravity times the, we have the density here, so we can use the density times the G. Okay. And times the pump head. So the power should equals to watts, so it's 56.77 kilowatt. And the problem also asks us to draw the hydraulic grid line and the energy grid line. So we'll start with the energy grid line. So it will be starting at the water surface, goes to the pump, like here. And the pump will pump it up, something like that. And the line will go down to the water surface again. So, and the energy grid line will have the difference with scroll 2G, something like this, and go up. And the velocity is the same, so it should have the same space. Okay. So the two lines should be something like that. Now let's look at problem 10.74. So we have a penstock connecting the reservoir and the turbine. So the Q of the problem is given, which is 2 cubic feet per second. The temperature is 40 degrees Fahrenheit. The height difference is 34 feet. The length of the penstock is 87 feet. And the maximum acceptable head loss here is 3 feet. So the HF is 3 feet. Okay. So and it's a commercial grade plastic pipe. So the the KS should be equal to 0. And we are asking to find the appropriate diameter for the pipe, and the size should be in even sizes like 2 inch, 4 inch, 6 inch, and so on. So for this problem, I'm gonna first assume a friction factor. For example, we're gonna say F equals to 0.015. Okay, then we're gonna use this to calculate diameter. So D should equals to 8 times FLQ squared over head losses times pi squared times G, and passing to the power of 1/5. Okay. And if we plug the numbers in, 8 times 0.015 times the L, which is 87 feet, times the Q squared, over the head losses. The maximum is 3 feet times pi squared times the G for the English unit is 32.2 feet per square second. So the diameter should be about 0.535 feet. Okay. So the next step is to find the velocity. V equals to Q over A. Okay. Q is given to cubic feet per second over A, pi over 4 times the diameter. Which should give us 8.899 meter per second. Okay. The next step, we're gonna find the Reynolds number, but the first thing we're gonna find the viscosity. For the viscosity of water at a temperature of 40 degrees Fahrenheit, the viscosity should be equal to 1.66 times 10 to the negative 5 feet squared per second. Okay. So our Reynolds number equals to V times D over viscosity. And we have the velocity. We had diameter. Viscosity is 1.66 to the negative 5. And our Reynolds number is about 2.868 times 10 to the power of 5. And we have the Reynolds number. We can use the formula for friction factor for smooth pipe for fully turbulent state. So 0.25 over log 10 of 5.74 over Reynolds number to the power of 0.9 and entire thing to the power of 2. And if you plug the numbers in, Reynolds number is 2.868 to the power of 0.9. The friction factor should be close to 0.0145. Now we have a second friction factor. We're gonna do the similar calculation and we're gonna find another D. D equals to, using the same formula here. So it's 8 times 0.0145 times 7 feet times 2 cubic feet per second squared over 3 feet times pi to the power of 2 times g. It turns into the power of 1/5. And this should give you 0.531 feet. Okay. And with this new d, you're gonna find new v. V equals to Q over A. Q is 2 cubic feet per second. A is pi over 4 times d, which is 0.531 feet. And the velocity should be 9.031 meter per second. Use the velocity and diameter to find the Reynolds number again. Times 31 feet over the viscosity. So the new Reynolds number should be 2.89 times 10 to the power of 5. And we're gonna do the calculation for the friction factor again. This will give you 0.145 again, so 0.015. Okay, so now we can see those two friction factors are the same, so we are pretty close to the final answer. So we can stop here. So D is 0.531 feet. And if we convert it to inch, it will be 6.372 inch. And we're gonna pick the close diameter in even numbers that is larger than this number. So it will be choose 8-inch pipe. Okay. Now let's look at problem 10.82. Both pipes in system shown an equivalent sand roughness Ks of 0.1 millimeter and flow rate of 0.1 cubic meter per second, and the diameter D1 equals to 12 centimeter, L1 equals 60 meters, D2 equals to 24 centimeter, and L2 equals to 120 meters. The problem is asking us to find a difference in water surface between the two reservoirs. So let's say 0.1 and the first reservoir, 0.2 at second reservoir. Okay, so we're gonna write down all the information we have. So first of all, we have the Ks equals to 0.1 millimeter, which is 1 times 10 to the -4 meter. And Q is equals to 0.1 cubic meter per second. D1 is 12 centimeter, so it's 0.12 meter. D2 is 24 centimeter, So it's 0.24 meter and L1 is 60 meter, L2 is 120 meter. The water temperature is 20 degrees Celsius, so the corresponding viscosity is 10 to the negative 6 meters squared per second. Okay. And we have like an entrance here, so we will have K lowercase e, K e uppercase E1, and here, and we'll have K uppercase E2. So we're gonna write down the energy equation. P1 over gamma plus V1 squared over 2G plus Z1 equals to P2 over gamma plus V2 squared over 2G plus Z2 plus all the friction and entrance and exit losses. For the 2 points, which is the water surface, so P1 is 0, P2 is 0, V1 is 0, V2 is 0. Okay, only leaves us the elevation terms and head losses terms. So C1 minus C2, which is the delta Z we need to find, is equals to the sum of head losses. So delta Z equals to, for the head losses, for the first part of the pipe is KE plus F1 L1 over D1 times V1 squared over 2G. Notice this one is for the pipe, is not for the surface, because although we said this is 0.1, this is 0.2, the surface velocity is 0, so please don't get confused with the pipe velocity. So this one here is the pipe 1, not the 0.1. Okay. So and for the pipe 2, I'm gonna use a similar thing. We have K1 actually it should be KE2 plus F2 over times D L2 over D2 times V2 squared over 2G, and the KE1 term is defined as V1 minus V2 squared over 2G. So this is now we need to find the F1 and F2. So we have a KS over D1 equals to one times negative 4 meters, and D1 is 0.12 meters. So the relative roughness is 0.00083, and V1 is equals to Q over A1, and Q is given 0.1 cubic meter per second. A is power 4 times diameter squared. So the velocity is 8.842 meter per second. And therefore the Reynolds number is 8.842 meter per second times the diameter over the viscosity. So give us 5.37 times 10 to the power of 5. Okay. So we have this all this information, and we use Moody's diagram. Can find F1 equals to 0.019, and we're gonna do the similar thing for the pipe 2. Ks over D2 equals to times 4 0.24 meter. The relative roughness is 0.00082. V2 is equals to Q divided by A2 which is 2.2 meter per second. The Reynolds number is 0 meter per second times diameter divided by the viscosity, which gives us a similar Reynolds number. So I use Moody's diagram again. F will be equals to 0.017. Now we can substitute all the numbers into the original of the energy equation, this one. So the delta C is equals to V squared over 2G is, for the pipe 1 is 8.842 meter per second over 2 times 9.81 times 0.5 is the entrance, because it's a sharp one. Okay. And F1 0.019 times the length of the pipe divided by diameter of the pipe plus the velocity squared 2g times plus 0.017 120 meter over 24 0.24 meters and plus the head loss from the larger pipe, smaller pipe to the larger pipe is the velocity difference. To the power of 2 divided by 2g. Okay, so the delta z equals to 44.5 meters. Now let's look at the last problem, 10.85. So this problem is similar to the previous problem. We have two reservoirs. We need to find the elevation. Instead of finding the difference, this one we're gonna find the elevation of the first reservoir. The Q is also given, and the diameter and length informations of the pipes are given as well. So let's write down the information we have. So Q is equals to 0.03 cubic meter per second. And the KS, it's a cast iron pipe, so the KS from table 10.4 should be 0.26 millimeter, which is 2.6 times 10 to the -4 meter. So the KE, which is the entrance here, is sharp edge, so it's 0.5. KC, which is contraction here, is 0.21 because this one is with an angle of 180 degree. D2 over D1 equals to 0.75. Okay. So this is from table 10.5. And the K, uppercase E here, equals to 1. Okay. The viscosity is 1.3 times 10 to the -6 meters squared per second for T equals to 10 degrees Celsius. So these are the informations we have. We're gonna do similar thing as the last problem, which is write down the energy equation for point 1 here. And point 2 here. Okay. P2 gamma V2 squared over 2G plus C2 plus the head losses term. So P1 V1 is 0, P2 V2 is 0. We only have the difference of elevations and head losses. So Z1 is equals to 110 meters plus the sum of head losses. So now we're gonna write down all the head losses term we need to find. So first we're gonna do the pipe 1, the first pipe here. It will be K entrance plus F1 over D1 times V1 squared over 2G. So this V1 is not the V1 in energy equation. Or we can see it's something like that. Should be easier to recognize the two difference of 1 and 2's. And for the second pipe, we'll have KC plus KE plus F2 times L2 over D2 V2 squared over 2G. Okay. So now we're gonna find F1 and the F2's similar as last problem. So KS over D1 is equals to 2.6 times 10 to negative 4 meter. D1 is 20 centimeter, which is 0.2 meter. So the relative roughness is 0.0013, and the velocity V1 equals to Q over A1, which is 0.03 over pi over 4 times the diameter to the power of 2, which is 0.955 meter per second. And the Reynolds number for pipe 1 is velocity times the diameter over the viscosity, which gives us 1.5 times 10 to the power of 5. Okay. With all those information, use Moody's diagram. We'll find F1 equals to 0.022. Okay, and for pipe 2, we'll do similar thing. And diameter of pipe 2 is 0.15 meters. So the rate of roughness is 0.0017. V2 is Q over A2. So the velocity is 1.697 meter per second, and the Reynolds number is equals to 0.695 meter per second times the diameter over the viscosity. Which gives us 1.9 times 10 to the power of 5. And we will use to move this diagram. F2 then equals to 0.024. Okay, so for the elevation, we're gonna use C1 equals 110 meter plus KE 0.5 times the F1 plus the F1 times the L over D plus 0.022 L 100 meter times the velocity V1 plus KC, which is 0.21 plus 1 plus 0.024 150 meter 0.15 meter times the velocity squared Okay, so the Z1 should be 114.235 meters. Okay, now we're gonna draw the energy grid line and hydraulic grid line. So we're gonna starting from the first reservoir, and because we have a larger diameter and the velocity is lower in the first pipe, gonna have something like this. Okay, and when it comes to the contraction, it will drop a little bit, then goes to the surface of second reservoir. And for the hydraulic grid line, because the first part have a lower velocity, it will be something like this, and second part will have a larger velocity, should be something like this. So the space here is smaller than the space here. Okay, so this is our energy and hydraulic grid lines.